Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, thank you very much, Inderjit and the other organizers for the invitation and for organizing such an interesting meeting. So I'm going to talk about something very, very basic, how to model data by a single subspace, but in a robust way. So first thing I'm going to do is just to have a very quick review on subspace modeling. I know that everyone here knows about it. What I will do in this review is just emphasize the most important properties of subspace modeling, so that if you want to develop a new robust subspace modeling, you want to actually follow the same kind of fundamental properties. And then I will present to you a very particular way to do subspace modeling. There are many other ways, and I'll mention them. But I will actually, here I will show you how this particular method satisfies the most basic properties of the common subspace modeling. And the emphasis of the talk will be on theoretical guarantees and implications. I really want you to get some idea about the theory behind it. And it's really, you'll see that it's really not hard to write a code and try it on real data. So our starting point is that subspaces are everywhere. And, the last several years I spent a lot of time on data where you have, I thought back then, it's not so interesting to model data by a single subspace nowadays. So I was looking for data where you have multiple subspaces and how to find multiple subspaces in data. And sometimes you even have, you need the local subspaces. And I mainly worked on data from computer vision because there you can really prove that subspaces exist. But sometimes I also like to work on more challenging data. And now I have a high school student to try to work on biological data with subspaces. Okay, and usually, we all know that modeling data with subspaces, we start with PCA. So let me, we all know about PCA, and Ravi mentioned it, but let me just make sure we're all with me. So, so in PCA, how do we model the subspace? For example, we want to fit a line to the data. We just want to minimize this energy, the sum of the distances of data points to the line among all possible lines. And we all know how to find it. Even Ravi mentioned it in his talk. We first find the sample mean, then we find the top D eigenvectors of the sample covariance, and this is the formula for the subspace. Okay, so this is the PCA subspace, which is the solution of this minimization problem. Okay, so just to speed up things, and let me ask you a very warm-up question, and to see you all with me. So is this a convex optimization? Okay. So yeah? Who thinks it's a convex optimization? Who thinks it's not a convex optimization? Okay, so only one person. Okay, so this is indeed a convex function, but we minimize over the set of all subspaces, okay? Over the Grassmannian. The Grassmannian is not a convex set, right? If you have lines in the plane, you can associate, let's talk about only linear subspaces, so you can associate them with a circle or half a circle. It's not a convex set. So this is not a convex minimization, but the solution behaves like a solution of a convex problem. That's why it's so successful, right? If the diff eigenvalue of the sample covariance is bigger than the D plus 1 eigenvalue, then it's a unique solution. And if not, it's unique up to some rotation. Okay, so actually this brings us to one of the first fundamental properties of this minimization, is that even though working with subspaces is working on the Grassmannian, which is not convex, still we have kind of a convex type solution, and that's why I really like PCA. Another important thing that it's very fast numerically, right? We don't do it by the covariance matrix, we do it by SVD, and we have fast algorithms for SVD. And the last property, which is very fundamental, comes from statistics. So if we have data sample from a certain distribution with covariance matrix sigma, and then we have IID samples from these distributions, and we have the sample covariance sigma n is the number of samples, we know that actually as n goes to infinity, the sample covariance converges to the underlying covariance, So if it goes to 0, and we also can quantify the rate of convergence. Okay, so this is a very basic result, and it has strong implications for PCA. Okay, so here I express it with a 2 norm. Let's just express it with a Frobenius norm, so we have to pay more with the dimension dependence, but it will 1 over square root of n. And now we can bound the difference between the subspace of the underlying distribution, so the subspace spanned by the top D vectors of the covariance matrix versus so this is projection on the subspace, and then projection on the subspace of the sample covariance, the top D vectors sample covariance, and we know the subspace that we estimate from the sample covariance still converge to the subspace of the covariance. This you can do by Davis-Kahan using this inequality. Okay, so this is really, really important. Why it's important? What does it tell us? That I can start with some distribution which is symmetric around the line. So this represents the underlying distribution. So it has a very, a lot of noise. But still, I can recover the line exactly if I have the large samples and I go to infinity. And even if the sample is not really large, I can still control the error. Okay, so this is very important property, because usually, when we try to do analysis of robustness to noise, we just take, we say let's have a very epsilon amount of noise, and let's do some perturbation analysis and show that we can recover the subspace up to error epsilon. And epsilon is really small. This is not the case. Here we can have very large amount of noise, and we can recover the subspace up to a really, really small error depending on our sample. Okay, and this is also related to the notion of sample complexity. So here, here I say, let's find the error given the number of samples. Sample complexity is exactly the other way around. I'm giving you the error, and then I want to find the minimum sample, so you get this error. Okay, so these are 3 basic things of PCA, and if I want to develop robust PCA, I want it to satisfy it. So I want it to be like convex-like solution, so I have this uniqueness, almost uniqueness. I want to have fast algorithm, and I want to have some nice convergence estimates. Okay, and as I said, I'm already talking about robust PCA because I don't like PCA. Why PCA is not cool enough for me? Because PCA is not robust to outliers. So this is a cartoon where our visual cortex sees a line here, right? But PCA doesn't see this line. This is the line that PCA provides us, and this is the underlying line. Okay, so when we have outliers, and sometimes you can even have more malicious outliers, PCA can be completely wrong. And and people knew about it for a long time, and there is a lot of literature on how to find robust PCA. So robust statistics go to long time ago, like at least to Galileo Galilei. But for the area of subspace modeling, I think most of the work starts in the 80s with Huber and his students and collaborators. And in the last several years, there have been many developments, especially in the last few years. There have been some new convex types algorithm, and some people will talk about them here, which actually inspired our work. Okay, so I will talk about a different kind of convex algorithm for robust PCA, but I'll try to mention maybe some of the other developments. So let me now discuss a very simple idea for robust PCA, and then I'll show you how it satisfies the property that we want PCA to have. So, the basic idea is that, PCA is based on L2 energy. Let's have an L1 energy. So instead of minimizing this, let's minimize this. Okay? The other basic idea, and you don't need to do it, but let me do it in this talk, is to also normalize all the points to the sphere. So maybe we can actually, and it should help a little bit with malicious outliers, right? So now all the points are on the sphere. Okay, so we try to minimize this while all the points are on the sphere. Let me also mention equivalent formulation to this problem. So here I minimize over the Grassmannian, over the set of all subspaces. Here, let me actually, instead of the Grassmannian, let me talk about the projection onto the subspace. So let me write down this energy. So the sum of the distances. And let me just clarify. When I say L2 to L1, I just mean that instead of the squares, it's power 1, but the distance itself is still Euclidean distance. It's not L1 distance, okay? So the distance between a point and the subspace is just the distance between the points and the projection of the points on the subspace, which is the projection onto the orthogonal component of the subspace. Okay, so now, instead of minimizing this over the Grassmannian, I can also minimize this over the set of orthogonal projectors. Okay, but anyway, this is a non-convex optimization because both the Grassmannian and the orthogonal projectors are not convex. And unlike this problem, if you study this objective function, you'll notice that it has many local minima. Okay, so this is not, and it's hard to minimize it unless you come up with some heuristics. Okay, so let me write down clearly this minimization. So I'll call this a matrix Q, and I'll minimize it over all projectors. Okay, so I want to minimize the sum of the norm of Q of X over the set of all projectors. Okay, so all symmetric metrics such that Q squared equal Q. And I also wanted to have, I'm talking about the orthogonal projectors, so I wanted to have rank D minus D. And because eigenvalues are even 0 or 1, so instead of saying the rank is D minus D, I'll say the trace is D minus D. Okay, so are you all with me? So this is the optimization problem. If I put 2 here, I'll get actually PCA. Okay, I'll find the orthogonal projector, and then I can read the subspace. If I put 1, I'm having some robust version. I have to prove it robust, but something that I call a robust version of PCA. But I don't know how to minimize it because it's a non-convex problem. Okay, so what's the most simple way to make it a convex problem? To find the convex hull of this set. Okay, so what's the convex hull of this set? So let's not change this linear constraint and this affine linear constraint. And now instead of Q squared equal Q, which means the eigenvalues are either 0 or 1, I ask the eigenvalue to be between 0 and 1. Okay, so this will convexify this set. It will actually be the convex hull. Okay, so now I want to minimize this convex function over this convex set. And let me also give you one more technical details that I don't need. I can replace this convex set by this one. So I can drop this constraint that Q is positive definite, because you can prove that the minimizer of this set is positive definite. Okay? So I'll minimize it over this set. Okay, so am I completely clear? You all know what is the problem I'm after for robust PCA? Okay, so before I move on, let me give you some picturesque terminology, and due to Joel Tropp. So Joel likes to call the problem of finding a subspace among outliers the needle and haystack problem. So you can think of this needle as a line among malicious outliers. And then he calls our minimization, he calls it the Reaper problem. Okay, and I will give you some Van Gogh pictures because he likes to draw Reapers. And I remind you that we minimize this energy over this set. So we get the supposedly the orthogonal projectors, and then we read the subspace by the kernel of what we find, or by the lowest D eigenvectors of this, of what we find. Okay, and let's also talk about the S-Reaper, because I said that, in this talk I'll actually initially normalize all data points to the sphere. So S is for spherical. Okay, so let me demonstrate how the Reaper algorithm or the S-Reaper algorithm can actually recover a subspace in theory. So let's have the setting with some Gaussian models, and later actually we go beyond the Gaussian. So we have some Gaussian distribution along the subspace. So it's some scaling on the projection on the subspace. So we have an underlying subspace L star of dimension little d. And in each direction we have some variance scaled by little d. And it should be clear from Ravi's talk why we do this scaling. Then we have outliers and outliers from the whole space. Okay, and again, it's a Gaussian distribution, and now it's scaled by capital D, the ambient dimension, okay, in all the space. And the theory will tell us that if we have data sampled from this distribution, so n inliers IID from this, and Gaussian and outliers from this, then you can recover. So if you have that the number of inliers is bigger than a linear function of the number of outliers, okay, with all these parameters, then you can exactly recover the underlying subspace by the S-Reaper algorithm with very high probability, and you have very nice expressions here because you're dealing with Gaussians. So there are some inequalities, and I'll talk about the proof, the ideas of the proof very soon. Okay, but the point is that we can recover, if we have this condition, the S-Reaper algorithm will work very well in this model. Okay, so let me just give you some cartoon here. So here we created the needle. We created a line in 100 dimensions, and we have 6 points on the line, okay, with this normal distribution, and then we have 200 outliers in the whole space, okay, and this is just a random projection. So of course, with random projection, you cannot identify the needle from the haystack. But now we take the lowest two eigenvectors of this of the solution of the Reaper, and we project it according to this, and now we can identify at least very clearly 4 of the inliers. Okay, and then I can also demonstrate a syringe and a haystack. So now we have some noise for the inliers, okay? So the noise is smaller than, so it's in all the space, but it's smaller than the noise of the whole outliers. And again, this is a random projection, and this is a projection on the bottom 2 eigenvectors of this of a solution, and you still see some separation from the haystack. Right, so I want to kind of, I don't want to just show you the theorem, I want to gain some understanding of the theorem. So let's actually have a deterministic theorem, and then, once you have a deterministic theorem, you can show with high probability that some condition is satisfied. So it will be, for me, it's more interesting to understand the deterministic theorem. So in order to have some conditions for this robust recovery, we need to know who are the enemies, right? What can make things wrong? So one enemy is when the inliers are strictly contained in a subspace, proper subspace of the underlying subspace. So suppose I want to find a plane, but all of the inliers, or maybe most of them, concentrate on a line. Okay, so of course I'll find the line, even though someone tells you, no, I have a plane for you, I will find the line. Okay, so I want to actually exclude this case. Another enemy is when the outliers don't fill the whole space. So suppose I want to find a line in R3, but the outliers are on another line, okay, or on a plane containing the original line. So I can take this whole plane, or the union of the 2 lines, and and say, okay, this is my subspace. Okay, so I can find a bigger subspace, and I still there's nothing wrong about it. I can't distinguish the outliers from the inliers. Another problem is when you have really, really big outliers, very large magnitude, and even if I scale everything to the sphere, it can still make a problem if all the outliers actually choose one direction. So even though they now have magnitude 1, they kind of contribute together, and I'll show you. Maybe talk about it a little bit later. So we really need to kind of fight all these enemies, and we actually do it very peacefully, so we just rule them out. So we need to have some conditions, okay? So how to deal with enemy 1, where you have the inliers are strictly contained in a subspace of L star. So we do it by working with a permeance statistics, okay? So what is the permeance statistics? So you look at the sum of all the dot products of x tilde is the normalization to the sphere. So all the points normalized to the sphere with a direction vector u. Okay, and I want to find the direction vector which minimize these dot products, so minimize the cosines of the angles. So actually, let me ask you, when the permeance can be 0, think of a data for which the permeance is 0. So if I have, suppose, I'm looking for a plane, but all the inliers actually are, so L should be, it's L star actually is a plane, but all the inliers are on a line. Okay, so then I can find a vector orthogonal to it, and these all will be zeros. Okay, so this is when I have really enemy 1, I can get permeance equals 0. So all the inliers are contained in a subspace contained in L star. So I call it permeance because inliers don't permeate L, right? And if the permeance will be large, we really have nice distribution of the inliers throughout all of L, so they permeate L.
When would you have a setting that you care about L, but all of your inliers are in a proper subspace of L? Wouldn't L then just be...
Right, but I want to have some theoretical setting, but someone tells me, okay, this is your underlying subspace and gives me distribution from this subspace. Okay, and I want to rule out wrong distribution from this subspace. Because my problem of exact recovery is as follows. Someone tells me L star, tells me distribution on L star, tells me distribution of outliers, and asks me recover L star. And I won't be able to recover L star if the distribution is wrong, if it's too concentrated on subspaces. Okay, so I just want to rule out, so this is for theoretical consideration, I just want to rule out all of these enemies. Okay?
But you assume that there's a distribution which is spherical Gaussian for both the inliers and outliers.
Okay, but now I'm talking about deterministic theorem.
That's it.
Yeah, and later I can get the Gaussian one. Okay. So I want to have large permeance. Otherwise, I won't be able to deal with enemy 1. What about enemy 2? So here we are lucky because we know the intrinsic dimension. So the condition that the trace or the rank is capital D minus D rule out what I called enemy 2. We still have a problem of enemy 3. So one way to deal with it was to the spherization, so all the points are on the sphere. But it's still not enough because I said, we can pick up a direction and put all outliers in a certain direction. So now let me introduce the linear structure statistics, which kind of reminds a little bit formally the permeance. So now we have power 2 instead of power 1. And instead of minimum, now we have a maximum. Okay, so now we pick a direction within some subspace M and want to minimize this quantity. So in practice, M will be very particular. So let's concentrate with M on the case where M is the whole space. Okay, so we don't need this projection. We just have all the normalized points on the sphere. And now, before we wanted to minimize the cosines or the dot products. Now we want actually to maximize them. So it will be maximized when the actually outliers will be very correlated, will be on one line. Okay, so then I can find a direction which maximizes it. So this is the direction of all the outliers which are very correlated. And it will be small when we don't have this kind of linear structure of outliers. They kind of spread out when we have control per direction. Okay, so we want the linear structure to be small and the permeance to be large. And our deterministic condition will be that the permeance is large and the linear structures of the whole space and the orthogonal complement of this are small in the following way. Okay, so given this deterministic condition, we can prove that if L star is the D-dimensional subspace and you have data points such that some of them are from L star and some of them actually from the rest of, the complement of L star, and you have this condition, only this condition, then the S Reaper problem will actually find the underlying subspace L star. Okay? So this is our condition. How much time do I have?
10, 15.
Okay. So I'll tell you briefly how to prove something like this, and then, how do you get the other theorem, the probabilistic theorem? You just, you have to show that this is satisfied with high probability. And it's kind of, people who are expert in comprehensive sensing kind of know how to do these things because you can see that the permeance and the linear structure kind of very, remind of incoherence function in comprehensive sensing. And there are different ways to show, to handle them in high probability. So here you can use Lagrange inequality and actually get a probabilistic theorem, but it's more interesting to see why this actually help you find the subspace. So I'll just give you the idea of the proof. So you want to show that this actually is the minimizer of this function, the sum of the norm of the q of x over this, and as I said, you don't necessarily need this restriction. So what you want to show that if I have this orthogonal projection with a true subspace and I have this function f, it will be strictly bigger for any perturbation delta than the original one. So let me remind you what is f, it's just the sum of all of these. And now which perturbation we want to include. So we only need to include the perturbation which actually, which we consider in this domain. So the trace has to be this, and they have to be bigger or equal 0 and less than or equal I. Now I can actually decompose the perturbation as follows. So there are 4 components, like, either the domain, so I can decompose the domain to L star and L star complement. I can actually decompose the image to L star and L star complement. So I get 4 components. In one of them, for example, it goes from L star to L star, the other one from L star complement to L star complement, and then other 2. And I can get some condition on these different components from the restriction here. Now let me remind you that I want to really prove this, right? That this sum is bigger than the other sum. That's what we had in the previous slide. So then, I'm not going to go through the technicalities, but you can check what happens when you deal with inliers. What's the difference for any inlier? To get a bound on it, what's the difference for any outlier? And you just need to control. So you want to control this sum. So you want to have actually the sum of the inliers plus the sum of the outliers. So you can just say the sum of the inliers is bigger or equal minus the sum of the outliers. And then you can control a term, you can control this sum by this sum and this sum by this sum. And it's very simple linear algebra, but I don't have much time, so let me skip it. And if you have a question, I'll go back to it. I want to give, instead of going through the very, the technicality, let me give you some overview. So let me now move on to a very different convex relaxation, which might give you some understanding what we are doing here. So now instead of, so here we talked about the convex hull, or we even dropped this condition, and we said, let's minimize over this set. Let's change it. So let me actually drop this condition. So I don't want to have q less than or equal I. Okay? I only want to have the trace to be constant. It's d minus d, but now I notice, I minimize this function, I notice that it doesn't matter which constant I put here. It's a matter of scaling. So I can just have traces equal 1. Okay? So now I will minimize this over this bigger set, but now what's good about it, I really don't know I don't need to know the intrinsic dimension. Okay, so in theory, and now it will be very more complicated theory because you need to address NME2 and so on, we can get exact recovery with no knowledge of this dimension. Okay, and you can all, before you had q less than or equal I, so you kind of suppressed the sort of singular values. Now you don't have this, so you can have sort of robust singular values. But what is really interesting about this, that I can view it as a robust, so the solution of this is sort of a robust inverse covariance. So what do I mean by this? So let's look again. I want to minimize this function as before, but over this bigger set. So let's go back to PCA. So suppose I have now a square. Okay? So I claim, and it's not hard to prove, that with this extra condition, the minimizer of this function over this new set is exactly the inverse covariance matrix. Okay? So now when I put 1, I can think of it as sort of as a relaxation, robust relaxation, and get a sort of robust inverse covariance. But actually it's interesting also because this case, when we have 2, because it kind of explains you why PCA behaves like a convex optimization. okay? Because I get the inverse covariance matrix and I'm looking at the bottom eigenvectors, okay? The bottom eigenvectors of the inverse covariance are like the top eigenvectors of the covariance, right? Which gives you PCA. So now I have a convex formulation which gives you PCA, okay? So that's why the solution of PCA is really behaves like, it's really a solution of a convex problem. Okay, and as I said, when we have power 1, it's sort of a robust version of the inverse covariance. Okay, so I think this is pretty fundamental, is, this idea that I didn't have a previous explanation why PCA behaves like a convex solution. Any questions about it? Okay. So actually the most important question is, there are so many other robust PCA, so let me give you some taste and see what other results do they have, okay? So let me summarize at least the case for the needle haystack when we have Gaussian distribution. I had, let me simplify the previous inequality. It says that the number of outliers is less than a linear function of the number of inliers, okay? So at least asymptotically, if the number of inliers over a number of outliers has to be bigger or equal than little d over d. Okay, so this is the amount of inliers per outliers that we can tolerate. Okay, let's see what other people have. So actually one of the pioneering work in the last several years is by Xu et al., and I think Xu is here and Konstantin is here. So they talk, it's a very different setting, but they talk about 50% breakdown point, so only getting ratio 1 between inliers and outliers, or 50% in terms of outliers versus the total number of points. 50% is what you usually get when you just have point estimation, like the median gets 50%. And if you don't take into account all the enemies that I talk about, you cannot do better. Let me just say a comment that for exact recovery problem, we actually get that this ratio has to go to 0, but it's a very different setting, so I won't get into the details here. My point is that, if you don't have all the assumption on the enemies, you cannot do better than 1, but if you have some assumption on the enemies, you can tolerate much better fractions. And in another important work, indeed, Xu et al., so it's again Xu and Konstantin, but now it's another third author, showed that you can tolerate a ratio smaller than 1. So in some cases, it's even better than ours, but when little d over capital D is really, really small, we actually gain. And this is actually, there are people who can even do better, so let me actually promote my ex-student, Teng Zhang, recently showed that actually you can really obtain this ratio with rather weak assumption. And let me tell you what actually it does. And if I have to, I kind of, we also actually have little capital D minus D, but I just for aesthetic reason, we wrote little d over capital D, and we had some hidden assumption there. Okay, so what does Teng do? Actually follows the Tyler's M estimator. So the idea is as follows. So we minimize the sum of the norm of Q of X. He will take the sum of the log of the norm of Q of X. So I kind of view it as a zero norm, as a zero norm is minimization, because in the limit actually the log is x to the p. So the limit of x to the p minus 1 over p when p goes to 0. And so but he needs to minimize over a set of positive matrices with determinant 1. So it's not convex, but he can show it geodesically convex. So one question is, okay, if you are in the convex region, or maybe even geodesically convex, is the ratio of little d over capital D or capital D minus D is the best one? Or can you obtain an even better one? I don't know the answer, but what I know from experience, and even there are some recent results, is that if you have some non-convex methods or heuristic, you can even do better when little d is much smaller than capital D. So one thing that I have a little bit of experience is just kind of nearest neighbors type method. So you can have sort of local subspaces and kind of get some idea. In very high dimension, you can get some idea about the best subspace. And we had some recent work in a very different context about local-based subspaces, and one of my collaborators, Arthur Schlam, told me that he did some very successful experiments with it, but there is no theory. Another idea with proofs is by Sultan al-Khattabi and Candes, where instead of looking at nearest neighbor, they kind of look at sparse neighbors. So you kind of express outliers by large dictionary. So the data points are sort of dictionary, and now you can express each data points by the dictionary elements and look at the coefficients, and you can recognize outliers by large dictionary coefficients. And now he can, so his signal to noise ratio, when I say SNR, I just look at the outliers as noise. So this is the relation he has, and this is what I showed you before. And you can see that when capital D is much bigger than little d, so they're doing better, but when they're comparable, we can do better. Okay, so I just want to emphasize, we're not doing the best thing on earth, and you can see in practice that when little d is much smaller than capital D, you can have many heuristics that work much better. Another result, just a theoretical result, that if you look at the minimizer of this energy that we were aiming to minimize, but you don't have an algorithm to minimize it because it's over the non-convex Rosmanian, and you have spherically symmetric outliers, then in theory you can, and at least asymptotically or with very high probability, but with very large number of samples, you can tolerate any positive ratio. But this is just a theoretical result. I don't know an algorithm which will obtain it. Okay, so far I kind of talked about our algorithm and how it's robust to outliers and all the different results. Now I want to say something why it's an attractive alternative to PCA. So, we saw that PCA had three fundamental properties. One is the convexity, which we also have here. The other one was the nice rates of convergence. So actually we also have nice rates of convergence for this robust PCA. It's a little bit harder to prove it. So with PCA we said, we had the underlying covariance, we had the sample covariance, they are closed. Now we have, instead of underlying covariance, we kind of have the continuous process. Instead of the sum of the QX, we have the integral over an underlying measure, and then we have IID from this measure, and we have the discrete quantity. And we can actually show convergence of the minimizer of the continuous, of the discrete problem to the continuous problem and control the rate. So if you recall, for the PCA we had 1 over square root of n. Here we have a little bit higher one. So we add epsilon, but then we have 1 over square root of n. And you can take epsilon to be small, but then your constant will be really large. So I can't take epsilon to go to 0. So this is a very recent theorem. We finished writing it at least 2 months ago, but I'll put it on the archive very, very soon. And this can also imply some sample complexity, at least when you use the Frobenius norm and the C-range and haystack model of the Gaussian that I talked before. So, for PCA with the Frobenius norm, you have capital D to the power of 2, and now we have capital D to the power of 2 plus epsilon. Okay. And just a comment, I told you that when you have power 2, you get the inverse covariance, and actually it's also give you a result on convergence of the inverse covariance. Okay, so I said, so now we also have nice results on the rate of convergence, almost like PCA. What about nice algorithm like PCA, like a fast algorithm? So you can show, it's not so hard to show it by differentiation, that a solution, so you can have an IRLS solution, so iteratively re-rated least square solution to this minimization problem. Okay, it's an L1 minimization, and it's very natural to do it. And I won't go through a process, but you get the following sequence. So and actually let me say something about it, because it's actually rather interesting. And here, I don't know if you recall my notation, but Q hat is when we only have, we minimize over symmetric matrices with trace 1. It's not the Reaper, it's the next thing that I talked about. So then it's much easier to minimize. And what does it actually mean? So if we have all these coefficients equal 1, let's ignore this. Then what do we get? The inverse covariance, right? And that's what we said actually we're approximating. But now what we do, we have some shrinkage coefficient. So in the limit, the inliers are in the kernels of this matrix. Okay? So now, if I have inliers, this, at least in the limit, will go to 0. Okay? So I divide it by a very small number. I have a regularization parameter, but I get very large coefficients for the inlier and very smaller coefficients for the outlier. So I have kind of shrinkage for the inverse covariance, and then to have trace equal 1, I scale it each time. And if you want to talk about the Reaper, you need to do some truncation argument and play with two constants, because you have two constraints. One is that you want the trace to be capital D minus D, the other that you want the norm to be 1. Okay, I won't get into the details here. So what you can prove is that you have linear convergence of this IRLS, which is attractive, and in practice you get capital N is a number of points, time D squared, where D is the ambient dimension. So this is comparable to full SVD. Okay, so if I use the full data and want to do SVD, at least non-random SVD, that's the complexity. Okay, so in this sense it's attractive in terms of relatively fast algorithm. So the conclusion is that I presented to you a robust algorithm for subspace recovery, and it had the three properties that PCA has. So it's convex, it's fast, and it has some nice robustness to noise. And it also, what might be attractive about it, that it's very, it's adaptive to many other problems. So I know, for example, Amit Zinger, actually from Princeton, who works on cryo-EM, told me that he could take this formulation and change L2 minimization that he had there to L1 minimization with this convex relaxation, and it works in parallel. So, and I'm sure there are many other problems. So for example, Ravi talked about how PCA actually is related to K Gaussians. Now you can think, for example, how this robust PCA might be related to other K distributions. There are many basic questions you can ask here. What do I like to think of? So one thing, I mentioned the result of Teng Zhang, which is interesting, and at least in terms of the subspace recovery, it gets better theoretical results. But in terms of the robustness to noise, this is not a convex problem, so it's really hard to prove anything there. Or in terms of the speed, it's also hard to prove things, but he told me that in practice, actually, it shows very nice results. So I'm kind of interested to see if there are also nice analyses for his results. His results actually doesn't adapt so easily to Euclidean problems like the one of Amit Zinger, because it's not exactly convex minimization, and it's a set of positive matrices. And another thing, I told you about that this notion of robust inverse covariance. So now, a very important topic in machine learning is actually and I think Pradeep will talk about it, is to find sparse inverse covariance and use it for graphical models. So I wonder if you can take some insights from this work and talk about both sparse and robust inverse covariance and combine them together using these techniques. So yeah, it's important for me to actually thank all the collaborators. And everyone here knows Joel Tropp, but there are three young and very bright people that actually I should mention. So Matthew Coudron, who is now a PhD student at MIT, was actually undergrad at Minnesota when he worked on it. Mike McCoy, who is PhD student at Caltech of Joel Tropp, and Teng Zhang, who is now a postdoc at the IMA. Yeah, thank you.
Questions? Do you have a fast algorithm for the first one also?
Yeah. So that's what I talked very briefly. So here, so that's what I write here. So you kind of run this iteration, but instead of doing this update, you do the following thing. So you have now two constants, C1 and C2. You'll have to solve them in the following way. So suppose you know them. What you'll do, you take C2 times Qn. You will truncate all eigenvalues which are bigger than this threshold. You just make them C1. Okay? And the way you'll choose these constants is that you just want the trace to be this and the norm, the two norm to be this. Okay, so it's a little bit slower than this because you need actually SVD at each iteration. So but it's a matter of constant. It's still ND squared, but you need to find so you need to compute eigenvalues each stage. But so it just so it's a bit slower than this, but it's not dramatic slowness. Yeah.
So the second enemy that you listed there was I think it was the second was when the outliers don't fill up the complement, the line, the proper subspace of the complement of the you're trying to recover. So does that mean? So I remember the intuition of that, but I don't remember the condition. Is the condition forced them to be force something on the empirical variance of the outliers? I mean, so suppose I have a mixture of two populations, because that's sometimes one of the problems that you have with robust PCA. So there, they might actually have that property, that they're in a proper subspace of the.
Okay. So one thing, a quick thing to do to deal with this enemy is to do initial dimensionality reduction. So you have full rank. Right? And you just do PCA and you take off all the the vector corresponding to zero eigenvalues.
That would always work.
So actually this is kind of necessary here, at least for this kind of algorithm. So right, because you have the inverse covariance. So you have to do this. Now in the case of the Reaper, you don't need to worry, because I claim that because you know the intrinsic dimension, you don't have any problem with this type 2 enemy. Okay, so even it can, so you reduce the dimension, but you can still have a problem, because it's possible that most of the outliers are on the line and only few in other directions. So for the Reaper, it's no problem, because you know what dimension you're looking at. For the other algorithm, when you relax it and you don't have the condition, the Q is less than or equal I, you're going to have a problem. You need stronger assumptions to prove that things will work in practice. So your distributions are more restricted.
Okay, so let's thank both the